Welcome everybody to week 5, day 3. First, a little bit of procedural announcements. There is an extra credit workshop today at 4, which means we'll be cutting lab time short a little bit today. I will be available to answer questions during the normal class time, but basically what we're going to do today is we're going to spend about an hour working on linked lists. I'm going to give you half an hour of lab time on RTX on, and then I'm going to pop over and start the recording for the Python workshop, which is worth extra credit points. I think 2 points is fair. Chop, who was asking for 10, I think 2 points is a fair amount. It's 2 letter grades on a homework assignment. And all you have to do is show up and write a little one-page report about what you learned. And there's going to be another one next week, and might even have another one the week after that. So you can stack up a lot of extra credit points in this class. I'm a firm believer in extra credit. If you can't make the workshop, it'll be recorded, and you have 1 week from the workshop to turn in the essay online. So basically, the deadline on Canvas shows today at 4 o'clock is the deadline. But I do that so it's just like on your calendar, you can see when it is. You have 1 week from 4 o'clock this afternoon to write a 1-page essay and turn it in, and then you get your 2 points. Okay. And then there'll be another one next week, and maybe another one the week after that, and then we're maybe even going to have a Linux installation workshop from Corelli. I think, is he online right now? I don't see him, but he was talking about teaching people how to install Linux on their personal computers. And can you get extra credits by giving a workshop? You absolutely can. And so the ACM, which is our computer science club on campus, gives workshops like a lot. Like, was anyone here last semester? Do you remember how many workshops we did last semester? It was a lot, I think. And I think I give extra credit for students attending Lawden's talk. He gave a talk at Fresno State. I think I gave extra credit for that too. It was like 10. Yeah. It's a lot. I'm a firm believer in extra credit because I think that if students want to go out of their way and like learn something new, especially like really anything, but it's, especially computer science related, but really anything. Like if you broaden your horizons, it just makes you a more interesting person. So like when I give a talk, it'll sometimes be on technical topics. Like I've got one on like hacking and security, and I've got one on Unix shell scripting, but some of them are on like Irish music and Japanese ukiyo-e art, the woodblock prints, and sea shanties and things like that. So yeah, I'm a firm believer in extra credit. I think it makes you a more interesting and well-rounded person, and it's good for you. And if you missed any points, you missed any test cases, then you can make those points up by putting in a little extra work and doing them. So, can you unlock down the lecture room? Am I in the wrong channel? The lecture room. We're in the lecture room. Oh, we're not in the lecture room. No. Wait. Phil did it for me. Okay, thank you. I was in the wrong channel. Look at that. Okay. So, release the people. Okay. Sorry about that. Yeah, I was clicked on the wrong channel. My head's not in the right place right now. I just got some bad news about a friend of mine in the previous class. So I'm going to be flying out to DC to visit him next Friday. So I'll keep you posted on that. I don't think next Friday I think is a vacation day, so I don't think I'm going to miss any class. It shouldn't impact this class at all, but I'll let you know. I'm going to be flying out kind of short notice to DC to visit him. Okay. So let's talk about linked lists. We're trying to say unlock. Let's talk about linked lists. So linked lists are always good to draw, and the reason for that is because the code just kind of looks like gobbledygook. When you're looking at code for linked lists, it's really good to sort of just kind of draw them out like this, right? If we have a linked list of integers, we can have every element of a linked list has an integer and a next. Call this one next. I usually don't need to write that. That's like the data there. I usually don't write that just because it's pretty obvious that's the pointer. It's an arrow. It's a pointer. And so we got a list holding 10, 20, and 30. Then this is what the list would look like. And the pointer here would be pointing at null. 10, 20, 30. Now, some invariants. In a singly linked list like this, a singly linked list has one pointer, a doubly linked list has two. A singly linked list typically has what's called a head pointer. The head pointer points to the head, and we've got a tail pointer that always points at the bottom. Now, the whole reason we do object-oriented programming is to preserve invariants. Preserve invariants. Things that must always be true about our class. So what must always be true about this class? Like, tell me about head. What must always be true about head? Could head ever be pointing like here, for example? Would that make any sense for head to be pointing like at the second element? Front of the list. Yeah, thank you, Sean. Head must always point at the first node. Okay? Head points to first node. What if the list is empty? What does it point to? Null pointer. Nullptr, as Arthur Dwyer pronounces it. Nullptr. Or null if the list is empty. What about tail? What does tail? What invariant must we preserve for tail? Could tail be pointing like up here? Null punter. Does tail also equal null pointer if the list is empty? I don't know. You tell me. Because you could test for an empty list by just checking to see if head is null if you wanted. Like, if technically only one of them needs to be null, but yeah, usually the invariant is it points at the last element. Or, if the list is empty, okay. They both point at the same null pointer. Well, remember, null pointer is just the number 0. One thing you have to always keep in mind when working with pointers is that a pointer is just an integer. It's just a number. There's nothing magical about them. If you do something like, if you say delete head, and let's say head holds the memory address 1234. What value does head have after you call delete head? It's going to unallocate this memory. This memory is in RAM somewhere. It's going to unallocate it. What happens to head when you call delete head? What memory address does it hold now? Not null pointer. It still holds 1234. Delete head releases the memory at that address in RAM. Basically, you can think of RAM as being reserved and in use or being free. If it's free, anyone can read and write to it. If you delete this and then you say like head points to data, you can do this and it's going to be reading and writing to that spot in RAM that's now been unallocated. And maybe somebody's going to come around and step on it and change the value. It's very dangerous. This is called a use after free. You freed the memory and then you used it. It's bad. It's super bad. Address sanitizer will pick it up. So delete head does not change head, actually. If you were to see out, head after this, it's still going to print out 1234. What you have is what's called a dangling pointer. So basically, you've deleted head. You've deleted the memory that head points to, but head is still pointing at that unallocated chunk of memory. So, yeah, that's a common mistake that students make, is they think that when you delete head, it does something to head. It doesn't. It just frees the memory the head points to. You guys understand? Can you place a value in that place of memory after it is unallocated? No. I mean, yes, but no. Don't do it. If it's been unallocated, if you want more memory, new it again. New blocks it off so that nobody can reuse that memory. If you ever write to unallocated memory, there's a good chance somebody's just going to take it and write to it, and your data all vanishes. New is like putting up fences, right? Like when you new memory, it's like, I don't know, let me draw a fence here. Like a corral, right? So when you new memory, it says, all right, this is your thing, and it returns a number like 1234. That's the memory address of this corral, and you're free to use all the memory inside of this corral as much as you want. But then once you say delete, 1, 2, 3, 4, then that fence gets torn down and anybody can come in and step on the grass and read and write to it as much as they want. That's what new and delete do. Okay. So, we're gonna do a couple things here. Are there any other invariants? Like sometimes we might have a variable called size, or something like that, where we like keep track of the size. I'm not going to worry about that right now. Any other invariants we need to worry about? They're going to be null if the list is empty. If the list has one element, they point to the same element. Yeah, but that's kind of covered already, right? So head's pointing to the first element and tail's pointing to the last element, and they're just pointing to the same one if they're the same one. Okay. So let's do this. So let's write a function called pop. Let's see. Let's move these invariants out of the way. Let's just move you kind of like up here somewhere. So let's write some code. Pop front. So if I call pop front on a list containing 10, 20, 30, which one of these three elements should be deleted? 10. Okay. So there's a couple things that have to happen. First, that memory's got to be deallocated. Second thing is head's got to move down here. Do you guys concur? I don't need to mess with this pointer because it's going away. That's about it, right? Those two things. Every time you make a line mark like that, that usually translates into exactly one line of code. Okay. So, what if we did this? What if we said head equals head points to next and delete head? There we go. Part 1, part 2. We're done, right? What do you think? What's going to happen? Is there a problem with this? You deleted the 20 node. Yeah, that's the problem, right? So I said head equals head points to next, so you're pointing at you now, then I deallocate you. And what's even worse is the head is now no longer pointing at anything. The old head is pointing at a dangling, unallocated chunk of memory. The entire thing is screwed up. Okay, the entire thing's screwed up. So this is not good. All right, let's try reorganizing this. Let's do it in the other order. Okay, so come in here and like move this over here. There. How about the code now? So the first thing we do is we delete the head, and then we say head is equal to head points to next. What do you think? Problem solved? You gonna work? So what's the problem here? Head points to next doesn't make sense after deleting head. Exactly. Once you've deleted something, you cannot use any of the RAM that has been deallocated. So if we deallocate this RAM, you cannot use any of that RAM. It's undefined behavior. It might work, it might not. It's terrifying. So, seems like we're stuck, right? It's like these are the two things we need to do. We need to like, I don't know, move head to next, and we need to delete it. Like, how do we resolve this unresolvable issue? It's been decapitated. So what's the solution here? What do you think we should do? Create a temp. Exactly. So let's make a new pointer, temp. And so we're just going to say temp equals head. So if head held 1, 2, 3, 4, temp holds 1, 2, 3, 4. Remember, they're just integers. That's all it is. It just copies it. There's nothing magical when you say one pointer equals another pointer. It's just copying the memory address. It's just copying the integer over. So temp equals head, delete head. How about we do temp equals, how about we do this instead? Temp equals head points to next. How about this? Cut out the middleman, all right? So temp is now pointing here. We delete head, and then we say head is equal to temp. How about now? So we create temp, temp points to head, points to next. We delete head, and then we say head equals temp. Yeah? You like that? So head's pointing at the top of the list, temp goes away. We don't care about that pointer anymore. That's been deallocated. Got no memory leaks, you know, it's looking pretty good. Okay. Already deleted head, can't use it. So this is a common conception, right? We've deleted head, we can't use it. Now, using head means doing something like this. Head points to data or something like that. Remember, all a pointer is just an integer. When you delete head, it doesn't change head. Head still has just the integer for this memory address. When you say delete head, this memory's been deleted, and then you can use head again. Head is just an integer, so we're copying the integer from temp into the integer that head holds. And so head is now pointing at temp. That's a-okay, actually. You can use head after you've deleted it because it's now pointing at something different, right? You're not dereferencing memory that's been deallocated. Yeah, good question, Michael. That looks good. Okay, so let's consider the case of an empty list. So what would happen if we try deleting off the front of an empty list? What's going to happen? You'd be deleting null. Yeah, that's actually okay. In the C++ standard, if you delete a null pointer, it does absolutely nothing. It's defined behavior, and the definition of deleting null is to do nothing. It doesn't crash your program. It's actually perfectly safe. You can delete null putter, as Arthur Dwyer puts it, all day long. No problem. It does absolutely nothing. It's defined as doing nothing. You do nothing. It's not segfault. If you delete a null pointer, it's fine. It just ignores it. It's defined behavior. It does nothing. It will segfault though. You're absolutely right, Holman. It will segfault, but it's not going to segfault. It's not going to segfault here. Okay, it's going to segfault here. Right there. It's going to crash. Do you see why? If you ever write code with an arrow, there should be something in the back of your head that says, but wait, what if that's null? Because if it's null and you do this, it kills your program. It will segfault your program. And so if you try popping off of an empty list, it will segfault your program because it tries accessing the memory here at null, and the operating system says, nope, you can't access memory around null. And it will segfault your program. Segmentation violation kills your program. So, do you understand? So you can't pop off of an empty list. That kind of makes sense, right? You can't pop off an empty list. So maybe, I don't know, how do we handle this? Do you know how the standard library handles this? How does the standard library handle popping off of an empty list? If head, yeah. So what you can do is say if head, or if you want to see if it's null, if not head. If head is null, if not head. If head is null, just like, I don't know, throw an exception or something maybe. You know, throw a runtime error. If you can read my handwriting, runtime error, blah, blah, blah. Or you can just like not do anything, just return or something. I don't know. If not head, return. If you tell me to pop off an empty list, I'll just, whatever, I don't care. ADT, yeah, so we don't know exactly what's happening behind the scenes with the standard library. So let's find out. Let's try it. Okay, let's try this. So, main.cc. Yeah, we need to talk about streams today too. A lot of questions about streams. I'm just gonna like comment this out, and we will get to this later. So let's make a list. Make a list of integers named lie that's initialized to 10, 20, and 30. And we are going to lie dot pop front. Pop 3 of them. It's not an empty list. Make sure this compiles, runs, absolutely nothing happens. Let's do it a 4th time. You see that? The official answer from the standard library people is to segfault. Like, they don't check. They don't check for null. Yeah, that was my reaction too. I'm like, really? You know, like, because I don't like writing code that segfaults. Let me tell you, like, it's just a professional pride thing for me. It's called defensive coding. Not everybody agrees with me. Obviously, the standard library people disagree with me. And the reason for that, and I've had a conversation about this before, is if you're going to be popping from a list, you're probably going to be checking to see if there's something to pop first. So if you're checking out here in main, you know, if there's anything to pop, then pop it. You know, that's the safe way of doing it, right? If you're checking it in main, then it's wasteful. It's unneeded for the standard library to do it. It's your responsibility to do it. If you want to shoot yourself in the foot and segfault your code by popping off an empty list, go for it. And it's literally one line of code. I know. So when I write my code checks for a null pointer and just like handles it some way or another. The standard library just is like, guess I'm gonna die now, and it explodes. And it's something that kind of bothers me, you know. And it actually bothered me enough that I was like, you know what I should do? I should write my own version of the standard library that doesn't segfault, because segfaulting's bad, right? And so I started getting into it. I spent a couple hours like researching. I bought a book a while back called Safe C++. Safe C++. It's a good book. It's all about how to make C++ not crash, you know, make it safe and reliable, kind of like Java. Didn't have any help for me, you know. So I started getting into it. I started like, you know, like, all right, it's gonna be a lot of work because standard library is huge. But I'm like, you know, I'll just focus on like list, vector, you know, things like that. Then I found it had been done already. There is a safe version of the standard library, and I was like, why don't you tell me about this? You know, and it's so bizarre is that there is actually a safe version of the standard library that does all of those checks, and they just don't tell you about it. Like, I don't know, like it wasn't in the Safe C++ book, I don't think. I could be wrong, I might have missed it, but this here turns on the safe version of the standard library. And I'll post that in chat for you. They had to struggle, so they want me to struggle. So if I run that, look, it gives you a nice error message. Yeah, look at that. In function list pop front error, attempt to access an element in an empty container. So nice, so nice. You know. Let's see if it makes any difference if I turn on debugging information. That might make a difference. No, it doesn't seem to. So yeah. Like, look at that error. Attempt to access. Wow, cool. It actually, you know, handled it, and it tells you, yeah, cool. You know, and so I started discovering all these things, right? That, like when I say nobody knows about them, obviously the people that made the safe standard library knows about it, you know. But like just in the general populace, I just realized, so like, fellow professors don't know about it. And so I ended up writing a paper for the SIG CSE conference, which is the International CSE Computer Science Education Conference. And I wrote a paper saying, hey, you know how C++ has this reputation of, you know, being like, you know, that unhelpful error messages, seg faults. Students have no idea why it's seg faulting. You know, it's kind of got this reputation of being a hard language to learn. I have figured out tricks that will make it as safe or almost as safe as Java. That you'll get error messages if you do something dumb, like popping off an empty list. And I wrote a paper on all these different things. There's a bunch of compile flags that, a lot of compile flags, that not all of them are useful in this regard, like the static libraries I should probably turn off. But like address sanitizer, UB sanitizer, undefined behavior sanitizer, safe, you know, turning on all warnings possible. Like there's a lot of things you can do, and I wrote Easy Peasy, a tool to actually search for the top 30 errors that students make in introductory computer science class. And I wrote this paper, and 2 of the people loved it, and they said, yeah, we should publish it. And the 3rd person says, you shouldn't be teaching C++. It's too hard to use. And I'm like, I know. That's why I'm writing this paper. Literally what you're complaining about is why I'm writing this paper. And he convinced the other 2 readers to not accept the paper. And I was like, yeah. 2 out of 3. It's like that one dentist that doesn't recommend the toothpaste, but he gets the other dentist to not like it either. Yeah, so, yeah, because it's my thesis. Like, if you have the right flags turned on and things like that, that, you know, C++ is actually it's fundamentally no different than, you know, Java, and, you know, it's probably even easier to write it in Python, because Python is not strongly typed. And the type system in C++ will pick up a lot of errors for you. So, that's what your uncle said. You shouldn't be teaching that to new programmers, and they're just so set in their ways, you know. It's like, but look, I figured out a way to make it easy for first semester students. Well, you shouldn't be doing that. It's just not done. Give me a break. I'd rage, yeah. C++ is for the strong, yeah. Yeah, I was just like, bro, what? Like, you're... So maybe I'll submit it again. This was like 2 years ago. I still haven't seen anyone using this stuff. So anyhow, so that flag, if you put that into your makefile, I recommend it. These flags right here, I would recommend you always use when you're doing development, like that. Address sanitizer, undefined behavior sanitizer, and the safe standard library are 3 flags you should always turn on in your makefiles when you're doing development. Only turn them off if you need speed. Like when you're failing that one test case due to being too slow, turn them off. Sure, you have my blessing then, but as you're doing development, you should always be making sure you're not double freeing, use after free, dangling pointers, any of this stuff. Okay. Yeah, I can post the paper if you like. But let's move on. So, I thought it was a good paper, but I'm biased. All right, so let's come back over here. So yeah, I personally, when I write code this way, I just say, yeah, if the pointer's null, return. But the C++ standard library people, for the normal one, say it's slow. This is unnecessary. You should be doing that already in your code. You should know better. And if there's one thing I know about programmers, it's that they don't know better. You know what I mean? Like, yeah. So I like writing my code safe and slow. The standard library, though, is not with that philosophy. Basically, Bjarne Stroustrup gave a talk in 2017 where he said that C++ should have like difficulty settings. You know, like you should have like beginner, like easy mode, and then he used an analogy of like a camera. Like when you take photographs with a camera, you can just put it on auto, you know, and it just picks the settings for you, and you don't really have to worry about it. And then maybe we start people on easy mode, and then we click the knob up to medium mode, and then when they're ready for like, you know, full speed ahead, no checking, we put it on like hardcore, you know, skulls and crossbones. Yeah. And his point is like, this is the default. You know, like when he gave his, it was the keynote speech at CPPCon 2017. His keynote was that we're defaulting to hardcore mode, and this makes it hard for new students because there's no bounds checking on arrays. If you do something wrong, it just seg faults, and we just say do better, don't write bad code, and that's not helpful. He's like, it'd be really nice if there was an easy setting for C++. And so I took that to heart, and I made one. And then, you know, the read library is part of that effort. Like, that came from Bjarne's talk in part. I mean, I've been kind of wanting to do that for a long time. But partly it's like, let's just make it easy for people, you know? And so I proposed it to the standardization committee, and they're like, there's no interest in that. I'm like, but Bjarne said so. No, okay, whatever. So yeah, it defaults, C++ defaults to death mode. And I think it should default to easy, and then when you need speed, like, turn that dial up, right? Turn off bounds checking. Boom. You know, once you're guaranteed that your code's bounds checked properly, turn off bounds checking. You know, knock yourself out. Yeah, Dark Souls. Yeah, exactly. And that's why C++ has such a bad reputation amongst that professor who just was highly offended by the fact that I teach C++ to first-year students. You can't do that. That's not allowed. Because it has that reputation of being a very hardcore, like, sucks to be you, you know, language. Okay. So that was pop front. Let's, how about we do, let's put this back here. How about we do push back? Let's add something down here. So tail is we're gonna add 40 to the end of this, all right? So what needs to take place? Is tail in a good spot here, by the way? Is tail here, like, I just added 40, like I wrote code, this is gonna be push back. And so I said, like, tail points to next. Tail points to next equals new list 40 and null putter. Oops, track my face off. So we set tails next to be a null new list. Its next is null pointer. Are we good? Are we done? Seems pretty easy, right? Are all the pointers in their place? Have we maintained our invariants? I find C++ to be a lot of fun. I do too. Like, I frankly just don't get all the hatred for it. I do get it, but it's because people studied it in the 80s and 90s. And when modern C++ came out and made a lot of things nicer, they just hated it already, so they didn't learn it. That's kind of where it all comes from. Romero, at least we aren't playing a roguelike. Imagine having to start your code over from zero if you segfault or miss a semicolon. I could do that, right? Like, I could write a shell script. So all I would have to do is just rm star.cc star.h. If I saved that, every time you failed to compile your code, it would delete all of your source code. Just one change, and you get roguelike behavior. Start over, write it from scratch again. Okay. So do it. Yeah. That would be absolutely horrible. You would get a lot of practice writing code, but you would, like, get ready to. Okay, it's not in there. Good. Yeah, it would be too evil even for me. Okay, so what is the invariant that we need to fix here? So tail points to next equals new list. What invariant needs to do it? It'll make it stronger. You're either going to quit or be a C++ god. That's funny. So what do we need to do? Do it for an easier project, yeah, like FizzBuzz. You just, like, hardcore FizzBuzz. You just have to get it right the first time. You fail any test case, it just wipes out your whole directory. Zeta. Zeta from scratch. Okay, so yeah, so the invariant we're violating now is the tails the tail's not being updated, right? So you have to say tail equals tail points to next. And we're good, right? Right? What is that big flashing? There should be in your head a light, a big red warning light like they use for like nuclear launch detectors. And that light should be like, what if that light goes off every time you use the arrow operator? Every time you use the arrow operator, this light should turn on. What if that pointer was null? Put some virtual heroes here. What if that pointer was null? What happens? Can I guarantee it's not null? What do you think? When will pushback fail? This code here is okay for most circumstances. It's not legible, but besides that, it's not problematic. Like if you have 3 elements in the list and you add a 4th one, the next is going to be set to be a new thing. The new thing's next is null. Tail gets set to the new thing. It's fine for most cases. There is, however, one case where it will segfault. And it's actually going to segfault pretty early. That arrow right there. When will that crash? When is this code here not going to work? If it's empty. Very good. Yeah, if tail is null, then when you say tail points to next equals new list, that's dereferencing a null pointer. Read, read, read. And this isn't like the other one. See, with this one, the standard library goes like, all right, that's your fault if you're dumb enough to pop off an empty list. That's your fault. Not our fault, it's your fault. With this one, when you call pushback, you have to be able to accept pushback working on an empty list, right? So they're going to have the if statement on that one, right? Because when you start, it's going to be empty. So we need to add a check for null. So let's just move it. No, it's not letting me do it. All right. So if tail is null, do you guys remember this? If not tail, that means if tail is null. So we're going to add a little check here first. And all this will be in like kind of the else block, right? So if tail is null, then tail equals head, because head's going to be null too, equals new list 40 and null pointer. Don't actually use a 0 there. It's bad practice. Use null pointer. Do you see that? So this handles the case of the list being empty. So if the list is empty, then head and tail both get set to the new element. It's going to create a new element where the data is 40. The next is null pointer 0. I just ran out of room on the screen to write null pointer out. And then if there is a list, then we can do this. So do you see that? That's a habit I want all of you to get into. Is that anytime you see that arrow, think to yourself, am I dereferencing a null pointer? Could I possibly be getting into a situation where a null pointer is going to be dereferenced? And if so, check. If tail, it means if tail is not null. If not tail, means if tail is null. Okay. Let's do one more. Any questions about this? Your first linked list assignment starts on Monday. These two functions make sense to everybody, or are you just frantically working on RTX in the background? Okay, now let's do a harder one. So we've got this. We got this list here. Let's say we're going to do pop back. So pop back is going to put us back the way before, right? For pop back, we're going to erase this. This pointer is going to become null, and tail is going to now point at this one. I made the changes in yellow. Every time you have a line or a stroke on the screen, that represents a line of code, usually. So we need to deallocate this memory. We need to set this fellow's next to be null. We need to set tail to be tail's previous element. There's one problem, which is that this is not a doubly linked list. If it's a doubly linked list, we'd just be able to move the tail backwards. As it is, we're going to have to start at the top. We're going to have to start at head and go to the next, go to the next, go to the next, go to the next, until we find the person one before the end. So that pattern I showed you yesterday to traverse an entire list, we're gonna modify that, because we're no longer going to traverse the entire list. We're going to sort of deliberately have an off by one error. We're going to stop one before the end of the list, and it's going to look. I'll just type in code, something like this. Okay, and then let's just do this. Head points to next equals list 20. Just leave that as null. And then head points to next. Do you not like that? Okay, all right. Equals points to next, points to next. Just building it by hand. We usually don't do this. List 30. So our list (10, 20, 30). Like that. Missing semicolon. There you go. Okay. Yeah, thank you. So there we go. We built the list by hand. Let's do the list traversal. This is the most important for loop, right? For list pointer temp equals head, as long as temp is not null. Temp equals temp points to next. Cout temp points to data, followed by an inline. Let's just verify that this code works correctly. 10, 20, 30. There we go. Okay, so you don't even need a tail in a linked list. Okay, fair enough. List pointer tail equals that. There. There. I'm just building it by hand rather than using functions to build it, which you normally do. That's true. Yeah, that would have wiped my whole thing out. Okay. So now we want to delete 30. And what we need to do is delete the last element, move tail backwards one, and set tails next to be null. Now, the trouble is moving it backwards we can't do in a singly linked list. So we have to do a for loop to start at the top and run to almost the bottom, but not quite the bottom, one before the bottom. So we have to stop when our next is tail. So we're going to start at the top and go until our next pointer double equals tail. When our next pointer is tail, we've reached the end. And we're going to create a pointer. So tail is down here. And we're going to make it so that when temp is pointing here, when temp's next equals tail, we stop. And now we've got the parent of tail. We can move tail back and set tail equal to temp, basically. So this for loop, though, is a bit tricky. So let's make sure we do this right. So And always sketch these things out. If you try writing code without sketching it out, good luck. Now let's do this. This temp equals head, while temp, and this won't work on an empty list either. If not temp, okay, there. Always, yeah. Every time I write a pointer like that, you saw I stopped. I'm like, wait, what if we have an empty list? Right? Stop. Check. If it's null, just quit. All right, cool. Okay, so while temp's next is not equal to tail. Temp is equal to temp points to next. So while our next pointer doesn't equal the tail, go to the next one. So we go to the next, go to the next, go to the next, and this terminates once temp's next double equals tail. Once temp points to next equals tail, then the loop finishes, and we are now the person above. Call this like parent or something. How about that? Parent is now the node above tail. Okay. So rather than calling it temp, we'll call it parent. Here. So this is our setup. We got parent. After we finish for loop, this is our setup. Parent's pointing at the parent of tail. Tail's pointing at the last element. And we need to get some stuff done now. So we need to delete this memory, set that thing to null, and move tail back. Okay, so we need to deallocate this memory. Delete tail. We need to set parents next to be null. Okay, and this is why I draw it out, because when you draw it out, you can actually see, like, look, this pointer is now pointing at nothing. It's called a dangling pointer. So when you sketch it out, you're like, oh yeah, I need to fix that thing, because this thing is not pointing at anything. That whole thing's been deallocated. And so currently, after we do the delete tail, tail's pointing at nothing, and parent's next is pointing at nothing. It's deallocated memory. So both of these things need to be cleaned up. Anytime you see a pointer like this that's pointing at nothing, they need to be fixed. So parent's next, this is next, right? Parent's next needs to be set to be null, and then tail needs to be set to be parent. Yep. Just with better handwriting. Alright, so we need to set this to be null. Oh, we did that already. Okay. And then we need to set tail equal to parent. This is okay. And it's okay because a pointer is just an integer. It's just copying an integer from parent into tail. And so tail now has the memory address of the last element. Parent then goes away at the end of the function or whatever, and all of our invariants are maintained. So that is what it takes to do. This is pop. There. Okay. What do you think? It's a little more complicated, isn't it? The running time of this is not good either, right? If you have 1 million elements in your linked list, how many elements do you have to run through to get to the parent of tail? If you have 1 million elements in the linked list, the only way of finding the 1 million, yeah, ish. Technically, 999, you know, 999,999, because you stop one before the last one, right? So you have to look at all of the 1 million elements except for the last one. You stop one before, but we don't care. Whenever you're talking about like big O and things like that, and we're gonna have a whole lecture on big O, probably next week. Whether it's 1 million or 999,999 doesn't matter. It doesn't matter in the slightest. What matters is that this is an order n operation. So it's order n. N is the number of elements in the linked list. So to print all the elements in the linked list is order n, right? If there's a million elements in the linked list, well, you get all million of them, you print them, right? To push at the front, though, like if we want to do a push front operation, and in fact, let's do this before we print it. Why not? Push front. Okay. So we just say head is equal to new list, putting in number -10 and the old head, just like that. And these need to be curly braces to be correct. There we go. So this order what? If I had a million people in the linked list, does it change the running time of this line of code here? Is this code any slower if I have 2 million than if I have 1 million in the list? Or is it just constant running time? What do you think? Is it constant running time? Yeah. So this is called order 1. And order 1 doesn't mean that it's like one operation, because there's a couple things happening here. We're setting data to be -10, we're setting the new person's next to be head, we're setting the old head to be the new guy. There's like a lot of things happening here, but it's a operation. The point is that this takes the same amount of time if the list is size 10 or 10 million. It takes the same amount of time. It's constant running time. It doesn't change. Whereas this one, if you want to pop off the back, then you gotta run through the entire list to find the parent of the tail, and then move the tail back. And you have to run through the whole list. That's an order in operation. If there's 1 million people in the list, it takes about 1 million. 2 million in the list, takes about 2 million. 10 million in the list, takes about 10 million. So, you guys understand basics of order in stuff? Well, like I said, we'll have a lecture on it, but these are sort of like computer science people just toss these terms out just like casually. It's just part of the language of being a computer science major. In the standard, in the C++ standard, they'll mention it. So, for example, if you want to know how long does list push front, pop front, why not? Pop front, complexity, constant running time. It tells you. The standard, it doesn't tell you how it does it. It's an ADT, right? But it does give you a guarantee of running time. So if you call pop front on a vector, it will take constant running time. It doesn't matter how big, did I say vector? Sorry, list. If you call pop front on a list, it will take the same amount of time no matter how many elements are in the list. Okay. Pop back, constant running time. Okay. Because they're using a doubly linked list, not a singly. Push front, constant running time. Now, if we go over to the forward list, a singly linked list, then pop front, push front. I'm not saying a pop back or a push back, right? And that's because they're order n operations, right? And they don't like doing inefficient operations. They're like, look, if you need to use that, just use a list. You know, the list has push front, pop back, pop front, where's the other one? Push back. So the regular list, you can push and pop on the front and the back equally, no problem. But for a singly linked list, they just don't allow you to push and pop off the bottom. You can only push and pop off the top. So, and that's because they don't like you doing inefficient stuff by accident. And erase, let's see here. If you're erasing n elements, then it's a linear running time. So if you're erasing 10 elements, it takes 10 operations. That's what it means by linear. That's order n, linear running time. Okay, clear. If you want to erase the linked list, if you want to erase an entire linked list, it's linear running time. That's actually much worse than a vector, right? If a vector is trivially destructible, then you can just deallocate a vector like no problem. But if you want to delete a linked list, you have to go through every element and delete each one. That's kind of the pain. Okay, so I'm going to stop talking now. Like I said, I've lectured on this for about an hour. You're going to get your first linked list assignment on Monday. And then I'm going to give you the remaining half hour of class to work on RTX on. If you have any questions, I'm going to put up some code showing how string streams work, because that's a very common question. How do you read an arbitrary number of integers off a line? And so that I'll just kind of toss up on the screen so you could admire it, ask questions about it if you like. Down here. Oh, I didn't run this, did I? Let's see if it works. Okay. Let's double check that this works. 1, 2, 3, 4, 5 lines. Boop. Linked list will be solitary. There. So pop back worked fine. Good. Of course it did. Why did I even doubt myself? Okay, so the code here open a file. Some people don't remember how to open a file. It's an IF stream, ends file name, like we'll call it like map1 or something, I don't know. And then if you want to read from a file, like that. So read line reads a line from a file. You pass it the file variable there, reads a line out of it. You then convert the string into a stream like this. And then you can pull out, this was for imaginary, but let's say that you're reading, a rectangle, right? The rectangle is of format double, no, it's an int. It is, yeah, int solid, and then double min x, min y, max x, max y. Pretend that I'm initializing all these. And then I go ISS into solid, into min x, into min y, into max x, into max y. And this, so like let's say that the string is like 0, 10, 10, 20, 20, 5, 6, 7. So the first number here means that it is not solid. This is the bottom left corner, 10, 10. The upper right corner is 20, 20, so it's a 10 by 10 square. And then that means lines 5, 6, and 7 of this file are children of this box. And anytime you have a non-solid box, it must have children. So if you have a double right arrow defined for a rectangle, you can read straight into it, absolutely. But this code's going to have to be in there somewhere, right? And so the question that everybody has is like, wait, if we have children, how many double right arrows should I do? Right? And you don't know. What you have to do is you have to just keep doing it. You know? You have to just keep reading until you run out of room, until ISS becomes false. So you do something like this, like a vector of integers named children, while ISS is true. Vector is not defined. That's right, we switched it out with list. So we can say int temp equals read from ISS, read one int from the stream. So that's going to read 5. Let's say the first time through it, next time through it reads 6, next time through it reads 7, next time through it returns an error. So if an error occurs, we're done, we break. If an error did not occur, then we add it to the list of children. Like that. And then this will, this is all the pieces you need for your rectangle. It's got the solid, it's got the minimum components, maximum components, and then this vector will have 3 entries into it, 5, 6, and 7. That's line 5, line 6, line 7. You all are children of me. The first line is 0, by the way. First line is 0. We're computer science majors, we count from 0. If you don't use read, what do you do instead? Then you do it the old-fashioned way. Integer temp, ISS into temp. So a string stream is a string you can read from like it's a stream. So you can treat this string that you read, and you can use getLine instead of readLine if you want. GetLine and readLine are almost identical. So how many possible parameters can read take? Just one, and it's a file. If you don't pass it any parameters, it defaults to CN. So if you don't pass, if you just say read, it just reads from the keyboard. If you say read and you give it a file, oh, it can also take a prompt, I guess. I forgot about that. Like you can say, please enter. No, actually that doesn't work with files. That only works with CN. Yeah, but you could be like, please enter your age, like that. You know, and that reads from the keyboard, and it prompts you. And if you don't type in an integer, it throws it away and reprompts you and things like that. But for a file, there's no prompting. It doesn't make sense to prompt a file, right? So it just takes a file like that. Do you need to use string for option 4 in RTX on? No, because for the manually entered rectangles, they're all going to be solid. There's no children in that. You're just taking one rectangle and intersecting them and see if they intersect. So all you need is minimum, maximum point, see if they cross. And yes, you don't need to do this for that. You use string streams when you have one line at a time, contains information, and it can have variable length. That's what we use this construction for. So this says while there's still stuff left to read out of this line, and then you just keep pulling one int at a time out of it until it runs off the edge. Once you run off the edge, it stops. If you don't do this, if you just used like CN for this or whatever, or just reading directly from the file, what happens is if you ask for the next integer, it reads it off the next line. And so you can't tell where the end of the line is. So what you do is you use readLine with string stream. These two lines here are like peanut butter and jelly, okay? You read a line, you turn it into a string stream, and then you read from the string stream like it's CN or something like that. You just read from it just like you're reading from a file or reading from the keyboard. Very useful tool. Very useful tool. I use it a lot. For splitting strings and stuff like that. Okay, so that is the end of our lecture for today. I'm gonna stop the stream now unless something else comes up. And I'm just gonna hang out and answer questions about RTX on. And then at 4, I'm going to dip over into the workshop. And I'll still be available for questions through the normal class time. And honestly, I'm available 24/7. I mean, just, let's be real. You can message me at any time and I'll answer you. Okay. So thanks, everybody. Have fun, work hard, and don't wait till the last minute. All right. Peace out.